So 2 quick stories. The first one is called Biomimicry, and it'll partially revolve around this. This is my new favorite carpet, but we'll come back to it. Biomimicry is a word coined by biologist Janine Benyus, who was asking literally, how do we solve problems by going back and asking nature, how did you do that? And so, anyone have any Velcro on? Okay. Velcro came from a European scientist discovering, these burrs are sticking to my wool pants. How can I replicate that process? Yeah, those little hooks. That's probably one of the best known examples of biomimicry. But there's some others that are pretty cool. Some of them have to do with structure, some have to do with process. This is from Europe. You know, if you ever think about the paradox of a flower is always clean. Leaves are usually clean, right? How do we try to keep surfaces clean? We try to make them as smooth as possible. But when you study the surface of a lotus leaf or the surface of a flower petal, what you discover are these little tiny microscopic dots, bumps on these surfaces. Dirt falls on the surface, and it teeters on those dots. And when a drop of rain hits it, the rain doesn't smear down the surface. It keeps its surface tension and rolls as a drop form down and takes the dirt with it and cleans the leaf. So this company in Germany makes lotus sand paint, which paint your building with that paint. Every time it rains, the facade is washed. The strongest ceramic known to man is Coors porcelain. It's used as the nose cone of ICBMs. It's made with heavy metals and very high temperatures. Stronger than that ceramic is the inside of the ceramic made by abalone shells in 48-degree seawater using protein and chalk. It's a matrix of protein surrounding chalk crystals. And if you break it, it will self-heal. And so there's a group at Sandia Lab who've actually figured out how to replicate that process. So you can take a substrate and drop it in a beaker of this solution, pull it out, and within several seconds you have several hundred layers of a clear, nearly unbreakable ceramic. So GM and others have been looking at, could we grow windshields for cars? Extending this thinking to buildings, termite mounds are really phenomenal. You know, if termites were the size of humans, these would be mile-high skyscrapers. And they're in these climates that have huge temperature variations, 30, 40 degrees over the course of a day. Now, what do termites eat? No, mushrooms. They farm mushrooms in the center of that mound. And those mushrooms have a temperature bandwidth that they can survive in of about 2 degrees up or down and very precise humidity conditions. And so this giant structure here is how they open and close passages in it, they bring moisture into it, and they regulate the temperature and humidity so it stays within plus or minus 2 degrees of 78 degrees in the core of that structure. And so Nick Pierce, an English architect working with Arup in Harare, Zimbabwe, built a complex called Eastgate that was substantially less to build and had 90% energy savings because it didn't require conventional air conditioning. It operates like a termite mound. So that brings me to this. Biomimicry can also get into systemic stuff as well. A friend of ours, a systems ecologist at the Smithsonian, Dr. Walter Adey, is probably the world's, he's the curator of algae, only at the Smithsonian would you have that title. He's probably the world's expert on how coral reefs function and formed. But he spent so much time on the coral reefs in the Caribbean that eventually the Smithsonian said, look, Walter, you're either there or you're here. And if you're there, you're no longer here. And so Walter had to figure out how to bring a living coral reef back to the Smithsonian. This is the 1970s. No one had figured out how to do that. And a coral reef is sort of the ultimate biological paradox. It is one of the highest concentrations of biodiversity and also one of the highest concentrations of biomass you'll find anywhere in the ocean. And yet the water in a healthy coral reef is gin clear and there are no nutrients in that water, right? That's like walking through a feedlot and not seeing any manure. So what keeps it clean? He discovered that on the back side of the reef you get mats of filamentous algae, sort of this hair of algae in the waves. And that algae, as it's moving in the waves, is stripping all the nutrients out of the water, that algal turf. And so he started building these constructed ecosystems using that. Well, it turns out it's also a really good way to clean up polluted water. And so they're building these systems now in Florida and to clean up portions of the Chesapeake Bay where you have shallow raceways with these mats of algae. And we got involved with Walter on this because the biomass out of those systems was either being fed to cows or thrown away. And it's producing these huge volumes of biomass on a weekly basis. Started looking at what's in there. It's using indigenous algae. And you have a class of algae called diatoms. And diatoms have a lot of fat in them. So they're really great for omega-3s and biodiesel. And the rest of the algae, you can make has a lot of carbohydrates, so you can make butanol or ethanol out of it. And to give you a sense of how productive these systems are, in Pennsylvania, I can produce per acre 3,500 gallons of fuel per year. To put that in perspective, that's 10 times per acre what I can get from corn to ethanol, or 6 times per acre what I can get in Brazil with sugarcane. Phenomenally productive, a byproduct of cleaning up polluted water. So here's where this comes in. One of the things they discovered in the course of doing this work was that the diatoms tend to break off, shear off from the hard substrates they were using at the bottom of their raceway. And what they needed was something that the diatoms could bind into that was longer and flexible, like you would see in an indigenous algal colony. So we made a phone call and connected Dr. Walter Adey at the Smithsonian with Dr. John Bradford, the Director of Research for Interface Carpet. So you are now seeing the world's first carpet made for algae. The long strands bind into here and don't break off, so it dramatically increases the production rate. And this fuzzy stuff, when you shop back off the algae at the end of the week, this is a refuge for the colony to regrow, and so the regrowth period is quicker and faster and also increases the amount of nutrients that you're stripping out of the water. And this is cheaper and lighter and simpler to use than the old substrate that they were using before. So this is another biomimic product.